Students, in the last lecture I have started the heterogeneous phase equilibria, and I discussed about the free energy composition diagrams for the different phase diagrams, different types of phase diagrams. So we are going to conclude that today, and so I showed you isomorphous systems, eutectic systems, and another isomorphous system with a miscibility gap. So today I am going to take up the peritectic phase diagram and show you how the free energy composition diagrams will look like, in fact can be used for obtaining information regarding stability of the different phases. As you know, peritectic phase diagram is basically based on the reaction known as peritectic, which is this type, where liquid reacts with another solid phase, here it is alpha, and produce another new solid phase called beta. This is an reversible type of reactions, so therefore we always write this. But we are interested in the forward reaction, that is liquid plus alpha going to beta. The phase diagram for such a system will look like this. First we will have a solid solution phase alpha, okay. So that is how it looks like, a little complex but not much complex. So liquid, this is alpha phase, this is gamma phase, liquid plus alpha obviously because we are connecting that, and this is the peritectic phase beta. You can see there is a horizontal line on the phase diagram that indicates a reaction, and this reaction tells you that liquid plus alpha reacts, produce beta. So therefore this will be alpha plus beta, this is basically beta plus gamma. Always in the phase diagram you will find that a peritectic reaction is most of the time followed by an eutectic reaction. So this eutectic reaction is liquid going to beta plus gamma, therefore this will be beta plus liquid, and this is liquid plus gamma. Okay, that is how the phase diagram looks like. Now let us draw the free energy composition diagram at different temperatures, and this is the Tp, okay. Tp is the peritectic temperature. Then we will draw another one here, which is the most, it cuts to many of the phase field, and then we will draw another one here. So therefore for the 4 temperatures we are going to draw the free energy composition diagram. One at temperature T1 is very clear, T1 liquid is stable, other phases are not stable at all. Then at a temperature T equal to Tp, that is the peritectic reaction temperature at which peritectic reaction takes place. Then at temperature T2, in which the tie line or the temperature line actually passes through a lot of temperature line, rather not a tie line, passes through a lot of phase field, and finally we will take another at temperature T3. Okay, let us draw that. So I need color chalks to do that. I will draw it one by one. Okay, so here itself I will draw temperature T1, this is A, this is B, similarly at temperature T2, the temperature Tp, where this reaction will occur. This is at temperature T equal to T2, and finally at temperature T equal to T3 Okay, so let us draw first at temperature T equal to T1. As you clearly see, there are only 4 phases here, liquid and 3 solid phases, alpha, beta and gamma. So in all these diagrams we need to draw the 4 curves, 1 for the liquid and 3 for the 3 solid phases. So for the liquid we are going to draw using a blue. So here liquid is stable phase, so liquid will be at the lowest part, this is GL. Okay. Now for alpha we are going to use G alpha, okay. G beta and G gamma, let us say G beta as a blue and G gamma we will be using a white color chalk. Okay, so I will just remove this temperature above so that you can see it very clearly. Let us not cross over, this always makes confusion. Okay, crossover means something else. That's how the 4 free energy composition curves will looks like. Okay, you can do it better in fact. Fine, so it's very clear liquid is the stable phase because the free energy curve for the liquid is actually at the lowest positions. Now I go to the at temperature Tp. At temperature Tp this reaction occurs, so therefore alpha, liquid and beta, all of them will be at equilibrium. But you see alpha is stable for certain composition range, then alpha plus liquid plus beta is stable in this composition range, then the peritectic horizontal, and then liquid is stable. Okay, so that's what you see here. So therefore it's very clear that we will have curves for the liquid alpha and beta crossing over each other because we have a region of liquid plus alpha and beta plus liquid also. So let us draw it for the liquid. Liquid is blue, so liquid is kind of like this. This is GL. Then alpha will cross over. This is GL. Sorry, G alpha, not L. And then you have beta. Beta will be also crossing over somewhere there. So liquid, beta is stable. So better to draw it like this. Oops. This will be, no, this will not cross over here. Okay, so this is G beta and Z gamma as usual will be above. Fine. So because there is a crossover, we need to draw tangents between these curves. So first thing we will draw tangent between 3 curves. So as you clearly see, it is difficult to draw tangent between 3 curves. So what we should do, you should basically move up this curve a little bit, then you can draw it. Otherwise it will look bad. Oops. Still it is not proper, so we have to bring it down a little bit. So I draw a common tangent between these 3 curves here, and I draw a tangent here between beta beta is the blue, the green, and the oops, yes, and the liquid curve. So this tangent here. So I have done two tangents. So now let us demarcate the regions specifically. So this is alpha, because alpha is stable here, you see here, and there is a common tangent between three: liquid is blue, red is alpha, and the beta. So therefore this is liquid plus alpha plus beta, and then you have a beta stable somewhere. It's not beta, this is liquid is stable, so beta cannot be stable. So let us remove that. It is not that, so it will be liquid. So what you do it, you remove this tangent will come next. So this will be liquid, so this tangent is fine. That's why I was telling that there's some mistake happening. So I'll do it, then I'll explain to you again. Okay, so this is the liquid. So as you clearly see here that liquid is the bottommost curve in the composition range from here to there. Okay, so that's how actually at temperature T equal to Tp will look like. Now at temperature T equal to T2, how it will look like? So you can see alpha plus beta, then beta plus liquid, then again liquid, then liquid plus gamma and gamma. So all the curves will cross over. So that's why it will look little. So let us draw it half, then otherwise it will look clumsy. So this is alpha. Obviously this will go like this, complete, and then beta and alpha will cross over here. So because there is alpha plus beta regime. Okay, then there is a range, then liquid and alpha beta will cross over. Let me write this one at the top. Liquid will be blue, so liquid will come somewhere there, then a little crossover. Okay, and then you have a gamma coming into picture. So what I will do, I will do a common tangent between beta and alpha, then common tangent between beta and liquid. Common tangent between beta and liquid will somewhere like this, and then as a common tangent between gamma and liquid. This is gamma. So you have a alpha, common tangent between alpha and beta will give alpha plus beta. Okay, this is beta. This is this is beta plus liquid. Beta plus liquid, and then gamma. Okay, liquid plus gamma. Okay, because there are regions in between the common tangents where we have the position of the curve at the lowest positions. Therefore, tangent between alpha and beta is giving alpha plus beta, beta and liquid giving beta plus liquid, liquid and gamma is giving liquid plus gamma. Okay, so relative dispositions will be little bit clear once you look at these positions. Here you see this tangent ends there and liquid comes down, beta comes down here, so therefore the tangent will be somewhere there. Similarly here the liquid comes down there, and then the tangent actually starts a little bit ahead. That's why it is like this. Okay, so at T3, let us complete it. At T3 again you have alpha plus beta, beta plus gamma and gamma. Only thing is that at T3 is liquid is going to be at a higher level. So liquid will be at a higher level. So let us finish it there. And then we will first draw the alpha. again it is better to do half because full will always make the life difficult. And then beta, so beta will be going like this, fine, and then gamma will cross over obviously. So gamma, so what I am going to do? I am going to do only draw a common tangent here, so beta has to be going down a little bit. Then only beta will have a, and then gamma beta will have like this. So you have alpha plus beta, beta gamma. So this is G gamma, this is beta, and this is G alpha. So what we have alpha plus beta, beta plus gamma, and gamma. Correct. So there are two tangents. Tangent may not look nice here, but it's there. And in between you have a beta region because this curve is going down. So therefore there will be two tangents. There will be no common tangent. One tangent between these and alpha, other tangent between beta and gamma. Okay, so that's how it looks like. And any further temperature down, nothing is going to change. Only the stability range of compositions are going to be changing. So you please practice yourselves, then only it will be clear to you. Otherwise, it is going to be creating more trouble. So we are not going further into the complex phase diagrams. You can also try monotectic and syntactic phase diagrams. These two phase diagrams will also be important because they involves liquid immiscibility. That's really part of your assignments. Fine. So you can actually try yourselves, then it will be clear to you. Now let me also continue the discussions. As you have seen, these phase diagrams are actually drawn at a 1 atmospheric pressure. Almost all the metallurgical phase diagrams are drawn at 1 atmospheric pressure. We don't change the pressure. In fact, that's why we have two axes. One is temperature axis, other one is a composition axis. And third axis, which could have been normal to that, we always ignore because we assume pressure to be constant. But in many cases, pressure is not kept constant. So it is better that we know what is the actual effect of the pressure on the these lines. Obviously, pressure will have effect both in terms of temperature of the transformations, also the compositions. So first we will look at what is the effect of pressure on the transformation temperatures. This is important for pure metals more because suppose in iron, pure iron, the gamma to alpha, the alpha to gamma transition temperature, alpha is BCC phase, gamma is FCC phase, actually depends on the pressure. Similarly, if you look at ice and water mixture, water ice transformation, that also depends on temperature of the transformation, depends on the pressure. So how we can bring it that effect? Well, we will discuss that in a mathematical manner first. First we know that G is basically H minus Ts, and we know the Gibbs free energy controls everything. So we can write down that this G basically let us write down total differential is equal to dH minus Tds minus SdT, right. Now this dG can be further expanded because H is nothing but E plus PV, and we know that this again further can be converted, made total differential right. So next step is to use the first law of thermodynamics. First law of thermodynamics tells you that these two parameters within the parenthesis is nothing but heat, del Q. So that's plus VdP minus Tds minus SdT, right. Similarly, we can again use second law of thermodynamics. Second thermodynamics tells you del Q is nothing but TdS. So TdS gets cancelled. So therefore we get total differential G is a function of pressure and temperature, that's equal to VdP minus SdT. Now to derive the effect of pressure on temperature, we are going to use this particular expression. Am I right? So let us suppose there are two phases, one is alpha, other one is beta. So we will write down the same expression for alpha and beta and then see what happens at equilibrium. So as you see, dG is nothing but VdP minus SdT. And we assume there are two phases, one alpha, one beta. So for alpha we can write down dG alpha or dG rather is equal to V alpha dP minus S alpha dt at any temperature, pressure P and T, right? Similarly for beta, this is G alpha, okay, otherwise it will. Am I right? And at equilibrium, we know that G of alpha must be equal to G of beta. It has to be at equilibrium because phi and H must be equal. And then we can write down dG of alpha will be equal to dG of beta. That means in top those two equations we can equate. So if I equate, what will happen? If I equate these two equations 1 and 2, by equating 1 and 2 we get V alpha dP minus S alpha dt is equal to V beta dP minus S beta dt, all at constant temperature pressure, because this equilibrium is happening at a temperature pressure which are given. So we can write down, we can simply write down V alpha minus V beta dP is equal to S of alpha minus S of beta dt. So therefore we can see dP by dt, or rather let us write other way, that helps you better. Dt by dP is equal to, so dP here it will go there, no, it is better write with P because you are all used to the Clausius-Clapeyron equation which you are going to derive. So that is nothing but S alpha minus S beta divided by V alpha minus V beta. So that's how actually the pressure will vary as a function of pressure will have that affect the temperature. So we can always write down in differential form in the other way. Okay. So as you see here, that effect comes as a function of change of entropy and change of volume basically. Correct. So we can modify the equation again further. How we can modify the equation? We can modify this very simply. Very simple, you can modify this equation. We know that G is nothing but H minus Ts, right? So therefore delta G is nothing but delta H minus T delta S. At transformation temperature, T equal to Tp transformation temperature, delta G must be 0 of any phase, okay, otherwise it will not transform. So therefore I get delta H minus Tp delta S is equal to 0. So therefore I get delta S is nothing but delta H by Tp. So if I plug in there, I get dP by dt. I can use this equation and write down delta S we can replace delta H divided by delta P multiplied by Tp. and this equation is known as Clausius-Clapeyron's equation. Okay, this tells you the effect of pressure on the temperature. So if I know the delta H, that is heat of transformations, if I know the volume change delta V, we can calculate what is the temperature change of these phase boundaries as a function of pressure. And this is used rather, okay, for pure iron. So let us take for the water. You know that when ice forms from water to ice, volume actually increases, okay. So as the volume increases, volume of the product minus volume of the parent phase, that is volume of ice minus volume of water, that is positive. But on the other hand, when you have ice transforming to water, this delta V is negative, because volume of water minus volume of ice is always negative, volume of ice is more. And this, because it is negative, therefore if I apply pressure, the melting temperature of water will go down. That is what happens if you apply pressure. Application of pressure will have a strong effect on the melting temperature going down, because this slope is negative. And that is why in the water phase diagram we will find the solid liquid transformation curve is always having a negative slopes. For metals it is not, metal is because delta V is always positive for the most of the metal transformations. So if one wants to use the effect of pressure basically on the transformation temperature, then this is the equation one needs to use, is to show you that. So in the next lecture I am going to talk about what is the effect of, basically curvature on the transformation temperature, and how even the solubility of these phases can be again mathematically proved as a function of temperature. These two effects we will look at it, because these mathematical formalisms are required for you to do different calculations.